I have developed the expression for the change in the area of an object as its temperature changes for you, and discovered, to much to our surprise or not at all to our surprise, depending on how you view such things, that the change in the area picked up a factor of 2 compared to the change in just one dimension of an object whose temperature is changing. So let me do a quick example here, first of all, before I go into 3 dimensions. And it's one that perhaps you've done sometime. You couldn't get the lid off of a glass jar. It's on too tightly. And the trick that your mother taught you, and that her mother before her taught her, and has been being taught to people ever since there were jars and there were lids, is to run the jar with the stuck lid on it under some hot water. And then that will loosen the top, is what you're always told, and then enable you to open the jar. Let's see if that really works. Hint, it does. So suppose you have a glass jar with a steel lid, okay, is held under hot water until both the steel lid and the glass have had their temperature increased by 30 Kelvin. Which is pretty typical temperature for water. I'm not increasing it to 30 Kelvin. I'm increasing it by 30 Kelvin. Okay. And a typical size jar will have a radius of, let's say, 10 centimeters. That might be a little big, but whatever. Calculate the final areas for each. Okay, easy enough. The idea here, so make a drawing. Okay, and so the radius is 10 centimeters, or at least the initial radius is 10 centimeters. Okay, and the whole thing is at whatever temperature, room temperature or something. You hold it under hot water. The water is at 30 Kelvin, sorry, 30 Kelvin higher than room temperature. And so as a result, the temperature of the glass and the temperature of the steel will both increase by 30 Kelvin. And as a consequence, their areas will increase. Okay, let's calculate those. I don't need a coordinate system, so we'll just solve. Okay, for the glass, the change in area for the glass is going to be the coefficient of thermal expansion for glass. Let's call that alpha sub G, times the original, I'm sorry, this would be 2 times alpha sub G times the original area of the glass. We're going to assume that the lid and the glass jar have essentially the same radius. If they didn't, the lid wouldn't be stuck. Or they're so close that the difference won't matter. Okay, so 2 alpha G sub G times the original area multiplied by how much the temperature is going to change. Okay, for glass, that's going to be 2 times, and I looked up the coefficient of thermal expansion for glass, and it turns out to be 9 times 10 to the minus 6 inverse Kelvin. And the original area is pi times R naught squared. Okay. And then the change of temperature is 30 Kelvin. I'm sorry, I should put in the numbers here. So pi times the original radius is 0.1 meters, sorry, squared. That's area. And then times 30 Kelvin. And I plug in those numbers and I actually calculated it and got 1.696 times 10 to the minus 5 square meters. Let's take a quick look at our units. 1 over Kelvin times Kelvin, the Kelvins divide out, so we're left with meters squared, sure enough. Okay, good. So I plugged in those numbers, and you might be surprised at the number of decimal places that I wrote here, but remember, these values are very small, and so we'll take 3 decimal places just so we don't miss anything. Whether I can actually defend all 3 of those decimal places is a worthwhile question, but in any case. Okay, so that's the glass. Meanwhile, the steel, which I'll do in blue just so you can tell the difference. So the calculation is exactly the same. 2 alpha sub S. This time, though, we need the coefficient of thermal expansion for steel. Okay, times original area times delta T. And so I looked that up, and steel has a higher coefficient of thermal expansion, which means that the dimensions change more with a given temperature change than does glass, which is the whole point of this, of course. So that turns out to be 12 times 10 to the minus 6 inverse Kelvin times pi, again, R naught squared, 0.1 meters squared times 30 Kelvin. And I plugged in those numbers, and I got 2.262. 2.262 times 10 to the minus 5th square meters, which is definitely larger than the increase of area of the glass jar. Okay, and by area, I'm talking about the area of the circular opening of the jar, right? Okay, so it's definitely bigger, and you know, and so that's what it means. The lid is now bigger. The area of the lid is now bigger than the area of the glass, and so that means its radius, its new radius must be bigger, which we could solve for if we really wanted to. This is the original radius, of course. But in any case, the area increase is noticeable and significant, and therefore the lid is now easier to get off because it no longer has the same radius as the glass jar has. And but how significant this is perhaps not obvious here, so let me make it obvious by doing this calculation slightly differently. Okay, the change in dimension of the glass, going back to the algebra now, is just 2 alpha sub G A naught delta T. Actually, I'm sorry, let me do steel here first. Okay, so the change in area of the steel lid is calculated this way, whereas the change in the area for the glass jar, the opening of where the lid goes, is 2 times alpha sub G times A naught times delta T. And the trick I'm going to pull here is to take the ratio of these, okay? And so if I do that, the ratio of delta S to delta G is equal to the ratio of how you calculate them. And when I do that, what happens? The 2's divide out, the alpha naughts divide out, the delta t's divide out, and again, it's probably obvious once you see it, that the ratio of how much their areas change is simply equal to the ratio of their coefficients of thermal expansion. And since alpha sub s was 12 times 10 to the minus 6 inverse Kelvin, whereas for glass it's 9 times 10 to the minus 6 inverse Kelvin. Once again, virtually everything cancels out. And we're simply left with 12 over 9, or 4 over 3. And thus the result is that the new area of the steel lid is 1 1/3 times larger than the area of the opening of the glass jar. And put in those terms, I think you'll agree that that is a significant change, at least percentage-wise. Okay, so that's that. And ordinarily, this would be a great stopping point, but the truth is, I've got just one more topic to say about thermal expansion. Let's go into the third dimension. Let's go into volume. It won't take very long, so I'll just go ahead and shove it into this recording. So when I did area, I said, okay, well, let me just multiply to get the new area, multiply the new length by the new width, and run through the math. And if I were and to do the volume expansion, I would, at least in principle, do the following. I would say the new volume is length times width times height, which would be original length plus delta L plus, times original width plus delta W times the original height of the object plus delta H. And then for each of the delta L, delta W, delta H, I would write in alpha times L naught times delta T, alpha times W naught times delta T, alpha times H naught plus WT, and on and on and on. And then I've got a product of 3 binomials, and so that's going to end up being lots of terms, right? And so what is this? 4 times 2, I guess that's 8 terms, something, I don't know what it is. Anyway, it's going to be a big, long, complicated algebraic problem, and there's no point in going through it, but I'll just hand wave my way through it. And the idea is I'm going to, again, replace all the delta L's with their, all the delta terms with their equivalents in terms of alpha, multiply everything through, make the same approximations that I made before, that alpha squared is going to be small, and then alpha cubed is going to be even smaller than that. So there's going to be a whole bunch of terms that I can neglect as being very small compared to just the terms that have only alpha to the first power. So we'll end up neglecting a whole bunch of things, and we'll go through a whole bunch of messy algebra. And the result will be finally that the change of volume is going to be, surprise, surprise, 3 alpha V naught delta T. Okay. If you really want to work your way through the algebra, it's not difficult. It's just tedious and time consuming, but it might be a worthwhile exercise. But that's what it is. Okay. And so if you're interested in the change of dimensions of an object and all 3 dimensions are comparable, this is how you have to do it. There's one last idea before I end all of this. And this is actually going to sneakily allow us to start transitioning our way, or at least it'll give us a stepping stone later for transitioning our way into talking about liquids. We've done gases. We're currently doing solids. Pretty soon we're going to do liquids as well. Okay, and it so happens that not just solids will change their dimensions as their temperature changes, but liquids will as well. Liquids, though, typically, not always, but typically are three-dimensional objects from the get-go. Okay, there are important exceptions, and we'll discuss some of those in class. But in any case, liquids generally are three-dimensional systems, and therefore this would, in principle, be how you would calculate it. But the fact is that liquids, as we've discussed, behave somewhat differently from solids, and the consequence is there is a very similar relationship for how the volume of a liquid changes as its temperature changes. Okay, and that expression looks like this. Delta V is equal to beta times V naught delta T. Okay, and the things I want to draw your attention to, pretty obvious. I put them side by side to emphasize it. But first of all, this expression here is missing the factor of 3. And second of all, of course, I've used a different symbol here, beta instead of alpha. Beta is also a coefficient of thermal expansion or contraction, but it is reserved for liquids. Okay, and for liquids, beta is still pretty small, as you might expect. So beta typically has values of 200 times 10 to the minus 6 inverse Kelvin, and for these are common liquids now, 1,000 times 10 to the minus 6 per Kelvin. Okay, so and this is simply a way of indicating that liquids, as a general rule, expand and contract much more when temperature changes than solids do. Okay? Which, again, if you think about it, is probably not all that surprising. So although the concept is really the same, we use a different symbol here for the coefficient of thermal expansion simply to be a visual alert that we're talking about a liquid typically rather than a solid. If it's a solid, we always, I guess, use alpha. If it's a liquid, we always use beta. And it's just, again, a visual cue of which type of object, what phase of object your system happens to be in. Okay, so that's that. There are lots of other properties of solids as well, other than just how their dimensions change with temperature. And again, please remember the objects can shrink in size as well as increase in size, changing temperature. So we'll talk about some of the other properties that solid objects have that are related to its temperature. And things are not related to its temperature, actually.